Okay, so we've covered a lot of ground in this chapter so far. We really started with this sort of basic idea of the structure, the electronic structure of atoms, where you have electrons that are sort of zipping around in space, like planets or stars, in their discrete orbital energies, and that gives rise to these line spectra where we get a specific emission of light or photons only at discrete frequencies instead of over a broadband continuous spectrum. That's where we started, and I think that's sort of the intuitive place that a lot of people start with the understanding of sort of the classical atom. But we've moved forward, and we introduced a little bit of work from this guy Planck and also Einstein and de Broglie, and we started to think about particles actually behaving like sinusoidal waves, just like that of photons. And that was all sort of brought together. This was a really dynamic time, actually. Most of this science was being done in Germany in the early 1900s. And this guy Schrödinger came along, and he was really the guy who took all of these puzzle pieces and started to think about a new type of physics to describe wave mechanics and probability. And he coined this the quantum mechanical model. And really, quantum mechanics was mostly concerned early on with thinking about how to describe electrons and particles inside of an atom. And you know, the simplest atom to think about is the hydrogen atom that has a single electron sort of zipping around it. That was the original idea. So how do we solve for, how do we build a mathematical model that can account for the line spectra that we see in the hydrogen atom? That was really the goal. So Schrödinger came along and he came up with this thing called the Schrödinger equation, which is really simple, but deceptively simple. Because it doesn't show any actual math. And what he said is he took this mathematical operator called the Hamiltonian, which is H, which is this big mathematical thing, and he used that to operate on this Greek letter psi, which I'd shown you before is really the description for the wave of this equation. And after doing that, what you get out of the equation is the energy of that electron or of that wave. And so Schrödinger was able to sort of go through this process where he was able to take the wave equation, this thing, and use his operation to solve this thing. And from that he would get this thing called a wave function, which we called this Greek letter psi. And this psi here could be used to model essentially the probability of finding an electron in any given region of space. And so psi squared, and it's not really important that you know this, but psi squared gave us the shape of where to find an electron in space. So that was really the great utility here. This shape of where to find an electron is a big deviation from the earlier models where we thought about these things as orbits. So in the earlier models we thought, you know, electrons zipped around in these orbits. This was Bohr's model. It had a discrete path, and it worked, but only in a really simple sense. Once we moved to quantum mechanics and thought about these things as three-dimensional standing waves surrounding the centroid or the nucleus, we transitioned away because we don't even have an electron moving in a path. Instead, we have an electron that's just standing still in a wave that's oscillating up and down in 3 dimensions. And so the quantum mechanical shape, we call not an orbit, but an orbital. And so you've probably all heard of the orbital. And the orbital is really the shape of the probability function that is predicted from the solution of the Schrödinger equation. So the orbital is not really a volume as much as it's a three-dimensional rendering of where the greatest probability you would have of finding that particular electron with that particular energy. And that's really what quantum mechanics did for us. And we'll talk in great detail in this class how we can have shapes of orbitals that are spherical, we can have dumbbell shapes, and we can have lots of higher order geometric shapes that are three-dimensional renderings of that probability function. Those are what we call orbitals. So the wave function itself, the sort of function, the wave mechanic function that defines that three-dimensional oscillation of a standing wave of an electron, that wave function is described by some constant numbers, some discrete numbers that we call quantum numbers. And some of this you're just going to have to take at face value until you take a quantum mechanics course or you take a higher level physical chemistry course, because we can't really get into the details of where the quantum numbers come from as much as they're used to help us describe exactly what the energy and the shape and the positionality of that particular electron wave is in the atom. And so these quantum numbers take on these letters, N, L, and M sub L, and actually M sub S as well, but we're going to focus on these first three quantum numbers first. So this N here is the principal quantum number, and we're going to start with that one. So just to show you very quickly, we won't do the math here, but I can show you how the quantum numbers, the combination of these three, N, L, and M sub L, how they inform the resulting psi or wave function of that particular electron. And so we can choose different whole number values for these, and I'll tell you why and what they sort of physically mean in a second, but they give rise to these very different functional forms of the wave, which give rise to different functional shapes of those standing waves and the energies. And so if you're interested in thinking about where all of this comes from, this is a great course to take in physical chemistry 2, or quantum mechanics, which is offered at the 400 level in the physics. So we'll start with the principal quantum number, which is N, lowercase n, sorry, not there. So principal quantum number, oops, that got dragged down. It is some positive integer, so 1, 2, 3, it's a whole number integer. And the key takeaway here is the size of n, the value of it, describes both the size of the orbital, psi and orbital really being synonymous with each other. Really, it's psi squared is the orbital. Anyway, orbital being the shape of the probability of where you'd find that electron, and the energy. So the larger the n, the principal quantum number, you have a bigger orbital space or volume where that electron can reside, and a higher energy level of that particular orbital. So if you've got a 1 electron atom, meaning something like hydrogen, that only has 1 electron, or ions that have all the other electrons removed, so there's only 1 electron left, then the orbital itself can be fully defined by n. Doesn't need any other subsequent quantum numbers. So orbital defined by n. If you have multi-electron atoms, which is everything else on the periodic table, then you need a larger n, and you are going to need other quantum numbers to help clarify and not be redundant. So it's important to make a point here that electrons, the 4 quantum numbers that electrons can take, those are sort of like a unique zip code for every electron. No electron inside of an atom can have the same set or redundant set of 4 quantum numbers. And we'll talk about this in a little bit when we get to the Pauli exclusion principle. Okay, so the first principal quantum number, really in summary, is size and energy. That's what it's telling us. And you can think of these principal quantum numbers sort of like layers. So n layers, sort of like shells on an onion. So n just being really the size and the shape. So n equals 3 is really like the third shell, the third size of that particular orbital. N has no bearing on the shape or the orientation of that orbital. It just tells us the size and its energy. That's it. So the second number or quantum number sort of in that unique zip code is this angular momentum quantum number, or the lowercase l. And the number, again, is only going to take on these whole numbers. This is telling us the shape of the orbital. So principal quantum number, remember, was telling us the size and the energy, and then couple that with the angular momentum quantum number and it'll tell us also the shape. Whether or not it's spherical or dumbbell, etc. So what numbers can L take? L can be any value from 0 to n minus 1. So for example, if we have a principal quantum number of 1, then that means L can only be equal to 0. If we have a principal quantum number for an orbital of 2, meaning it's in the second shell, then L can either be 0 or 1. For n equals 3, L can be 0, 1, and 2, anything up to n minus 1. So we often consider L to be subshells because n is the shell, that's sort of the big onion picture, and then these L's are different subshells that fall underneath whatever that n value is. So for n equals 1, we can only ever have L equals 0, that one subshell. For n equals 2, we can actually have 2 subshells. For n equals 3, we can have 3, etc. Okay, so let's push this screen up a little bit. So let's think about the possible L options that we'd have. So L can have or gets defined with some different notation that you've probably all seen before if you've taken a chemistry course. And it's actually pretty antiquated. So if L has a value of 0, then we actually call that orbital an s orbital. And this comes from some really old spectroscopy back in the 1900s. So this s doesn't really mean anything to us in modern days. So in this case, this L subshell, we would call that an s orbital. And in reality, because this is an n equals 1 orbital with an L equals 0, we'd actually call this specific orbital 1s. 1 coming from the principal quantum number, and s coming from the fact that this is an L equals 0. If L takes a value of 1, then we call this a p orbital, a p-shaped orbital. So that would be in this case. So this would be a p orbital, this would be an s orbital. So here we could have n equals 2, we could have a 2s or a 2p. That's what these two L options would give us. If the L value is 2, then we call that a d orbital, so it's a totally different shape. Again, all of these different L values are referring to different shapes of the orbital. So this would be our d orbital, this would be a p orbital, and this would be an s orbital, all underneath the n equals 3 shell. This continues, though we don't deal with them that much in this class, to be L equals 3. Those are f orbitals for our g orbitals. Okay. So let's summarize this with an example really quick. If we've got, say, an orbital that has n equals 3 and L equals 2, what type of orbital would that be with this notation? We would call this L2 would be a d orbital, and the big shell would be 3, so we'd call this type 3d orbital. And so these two principal quantum numbers, 3 and d being just a proxy for L equals 2, give us information about the size of the orbital, the energy of the orbital, and then the d tells us about the shape of the orbital. And so we've got quite a bit of information, but there's still one more quantum number that we need to really fully define these orbitals. So the final quantum number that we'll talk about, at least in this first set of three, because there's actually 4 quantum numbers, we'll talk about the 4th one in a little bit, but the 3 that we need to define, the energy, the size, and the shape and orientation of the orbital, includes this last one, which is the magnetic quantum number, and we call this m sub L. And m sub L, the magnetic quantum number, if n, the principal quantum number, tells us the energy and the size, L tells us the shape, then the magnetic quantum number tells us the spatial orientation. So shape doesn't tell us how that is oriented in space, so we need this last quantum number to tell us how this is aligned with the x, y, and z Cartesian coordinate axes. So m sub L can take on values anywhere from -L to +L, and again, these all have to be integer values, and that's going to be the case for all 3 of these first 3 quantum numbers that we talked about. So for each subshell, in other words, for each shape or L value, that means that there will be 2L plus 1 spatial orientations that can exist. That 2L plus 1 just comes from this range, from -L to +L. Let's do that with a couple examples here. So if we have L equals 0, so that's an s orbital, then m sub L can only equal 0, right? Can only equal -L to +L. If we have L equals 1, then m sub L can equal -1, 0, and +1. So we have 3 different orientations, which would be 2L plus 1. 2 times 1 plus 1 is 3. Let's scroll this up. If we have L equals 2, then m sub L can equal, and I'm just going to write this shorthand, plus or minus 2, comma, plus or minus 1, and 0, which gives us 5 different orientations. This gives us 3 different orientations, and this gives us 1 orientation. Okay, so let's think about this for a second. So when we're talking about the possible orbitals, remember that an orbital is really a 3-dimensional probability function. It's the probability of finding an electron in some sort of shape or volume. So this table plots all the possible orbitals that could exist with the different quantum number sets that are available to us. So if we go first to the first quantum number, which would be 1, and we look at, based on the rules, we can only take L values from 0 up to n minus 1. So in that case, L can only be 0. And m sub L is going to be everything from plus L to minus L. And if it's 0, then that's also going to be 0. And so we're going to call this a 1s orbital, because L of 0 is s, 1 is p, 2 is d, 3 is f, and 4 is g. So we've got this 1s orbital. It only has 1 orbital in that subshell, meaning 1 orientation, and that means there's only 1 possible orbital that could take on an n equals 1 principal quantum number. That's going to be the 1s orbital. That's it. So if you have a orbital that has a principal quantum number of 1, you can only ever have 1 flavor of that, just the 1s. There's no other iterations. You've only got 1 possibility. Okay, so that changes once we get above a quantum number of 1. So if we're at quantum number 2 here, then we can have two different shapes, right? So N is going to be size and energy, L is going to be shape, and then M sub L is going to be orientation. Those three things combined give you the unique zip code of that particular orbital, giving you the size, energy, shape, and orientation of it. So if we have n equals 2, that means we can have two shapes. We can have S and P. And then of this S orbital, we can only have one orientation. And that should make sense in a second. I'll give you some illusion here. An S orbital is this spherical orbital that looks like this. If you have a sphere in space like this, if these are sort of X, Y, and Z orbital or Z orientations, a sphere is symmetric in every orientation, so it can't have more than one orientation. It looks the same no matter how you look at it in three-dimensional space, which makes sense. So for every S orbital, which is an L of 0, you also only have this one orientation, because you can only have a sphere in one orientation. You can't rotate it and have a different shape. So that gives us this 2s orbital, which only has that one orientation. But the p orbital, which we'll talk about in a second, a p orbital looks like a dumbbell, like this. And so a p orbital does have orientation dependence, right? It could be aligned with any one of the three Cartesian axes. It could be aligned with the y, the x, or the z. And that's what each one of these magnetic quantum numbers means, the -1, the 0, and the +1. So we could have a dumbbell in the vertical direction, a dumbbell in the horizontal direction, and a dumbbell pointing into and out of the screen. That gives us three possible orientations, which means we have three different flavors of 2p orbitals. So cumulatively, within that n equals 2 shell, we have four possible orbital shapes that could be taken on. We have this 2s orbital, and we have three different 2p orbitals. Those three different 2p orbitals, again, are coming from the three different spatial orientations of the same shape, the p. Okay, let's go to the n equals 3 orbital. Now we've got all three of these different shapes. So we've got the S, the P, and the D. The D we're going to talk about in greater length in a second, but just know that D has several different shapes that it can employ. The s orbital, as always, has only got one orientation because it's a sphere. The p orbital has three orientations, as always, because a dumbbell can orient in those three axes. It turns out that the d orbital has 5 different orientations that it can exist in. And so we end up with one of the 3s orbitals here. We've got 3 of the 3p orbitals, just like we had above with the 2p, and we've got 5 possible d orbitals, 5 different orientations. So cumulatively, we've got 9 different orbitals in the n equals 3 subshell. And I won't go through the n equals 4, but this is the same rationale. We've got all 4 different shapes now, S, P, D, and F. We've got 1, 3, 5, and 7 different orientations of these different shapes, which gives rise to 16 possible orbitals that all fit within the n equals 4 subshell. Okay, so think about this for a second. This is sort of a brain melt, but when you have electrons, these electrons are going to start to fill into these orbitals, right? These are just probability functions of where that electron can exist, but an electron can't exist anywhere else. That's the whole idea of discrete or quantized energy levels or orbitals. And so the electrons have to fill these things up. So it means that if you have electrons that fill all the way up to, let's say, the end of the 3p orbital, or the n equals 3 orbitals, and they fill all of the sp and d orbitals all the way up to, let's see, these 14 different shells. You have to think about that atom then, where the nucleus is, and you're going to have all of these different shapes and orientations attached on that same exact atom, with electrons residing in all of those places. So you get a superposition of all of these different shapes on that one thing, or on that one atom at any given time.